So when we last left off, we talked about the Aldol reaction and Aldol condensation. And we talked about how we can use the Aldol condensation for both inter and intramolecular reactions. So just to refresh our understanding of the Aldol reaction, let's take a look at the following problem, where we're asked to predict the product from the following reaction and then draw a mechanism for each reaction. So in this case, we're treating this diketone with sodium hydroxide, which is a base. And then we're treating the product from the first reaction with hydrochloric acid, and we can even add a little bit of heat. So let's start off with a broad sense of what's going on here. So sodium hydroxide is a base, and these ketones have acidic alpha protons. So if we're thinking about predicting the product from this reaction, what would the first step be in this reaction? What's the first thing that we're going to see? We have a base, such as sodium hydroxide, and we have acidic alpha protons. So these are textbook conditions for an aldol reaction. And because this molecule is symmetrical, we really have a choice. Are we going to deprotonate position A or position B? Now, for intramolecular reactions, it's important that you really label your carbons. So this is a 9-membered ring. And what I like to do to gauge whether a intramolecular reaction is reasonable is I like to draw a line between my nucleophilic enolate carbon and my electrophilic carbonyl. And then I count my ring size. So this is a 5-membered ring. That's reasonable. If we tried to form a aldol condensation product from position A, 1, 2, 3, 4. So when we talked about intramolecular reactions and when we talk about ring-forming reactions in general, is it easier to form a 5-membered ring or a 4-membered ring? Yep, the 5-membered ring is preferred. So then we're going to want to deprotonate at position B. Okay, so let's draw that out. One, two, three, four, 5, 6, 7, 8, 9, 6, 7, 8, 9. Okay, I always end up having trouble drawing these no-name ring systems. Okay, so we established we're going to deprotonate the following alpha position to make our enolate. One more carbon. Okay, so we've generated our enolate. Now that we have a nucleophilic enolate, now that we have our nucleophilic enolate, what's going to happen with our enolate? Do we have an electrophilic atom present? Is there an electrophilic atom in this molecule that our enolate can react with? exactly right. This enolate can react with our electrophilic carbonyl carbon. And now what I'm going to do is I'm going to note that we're going to form a 5-6 ring system. Okay, and now I'm just going to label my carbons. So carbon 9 and carbon 5, that's our key bond that we're forming on this chart. My carbonyls at carbon 1, 2, 3, 4, and at carbon 5, we've just formed a carbon-carbon bond, so that's where we'll draw our alkoxide ion. Does everyone see how we can label our carbon atoms to draw out the ring system that we formed? This method of making a guide for what bond we're forming and then figuring out what ring system we're making is very helpful for properly drawing the product from these intramolecular reactions. Does this bond forming step make sense to everyone so far? Again, for intramolecular reactions and your intramolecular reactions, you're going to need to be very careful to label your carbons. Okay, so we treat this with sodium hydroxide under basic conditions. Because sodium hydroxide is a weak base, there's going to be a little bit of the conjugate acid water floating around. So we'll be able to protonate. And we now have this beta hydroxyketone. Now, traditionally, this beta hydroxyketone would be pretty hard to isolate as a stable species. This entire aldol reaction is in equilibrium. So, in order to drive this equilibrium towards the products, we're going to treat this compound with hydrochloric acid. What does hydrochloric acid do? So if we treat a beta hydroxyketone with strong acid and heat, what does this do? What are these conditions trying to accomplish? So we have our initial aldol reaction where we formed our carbon-carbon bond. We treat this product with hydrochloric acid. What does this strong acid and heat do to this beta hydroxyketone? So up until this point, each of these steps are reversible, right? But for the aldol reaction, one way that we drive the reaction to completion is via dehydration and formation of an enone. So in this case, if we take this beta hydroxyketone and we treat it with hydrochloric acid and heat, what does this accomplish? What are we trying to do here? It's a dehydration reaction, exactly right. We are removing water to generate our desired enone. So we're going to protonate our alcohol. From here now, we can eliminate our leaving group and kick out water to form the enone. And this is the key step that drives this equilibrium towards the products. And this gives us our desired 5,6 fused enone. Does this general mechanism for the aldol reaction and dehydration make sense? Okay, perfect. So now what we're going to talk about is a relative of the Aldol reaction. This is another carbonyl condensation reaction, this time involving esters. This is known as the Claisen Condensation reaction. It's the reaction of two esters having an alpha hydrogen with one equivalent of base to yield a beta ketoester. So we are in effect forming the following carbon-carbon bond with the loss of ethoxide. This is a wonderful method to prepare beta ketoesters. You can think of this reaction very similar to the acyl substitution reactions that we've learned previously. We know logically that, for example, if we have an ethyl ester and we treat it with a nucleophile, we'll see attack of our nucleophile. We'd make a tetrahedral intermediate, and then we have a choice. We can either kick out our nucleophile or we can lose ethoxide, right? Does this general carbonyl condensation mechanism look familiar to everyone? Does this general carbonyl substitution mechanism look familiar from previous chapters? We've seen this in the Fischer esterification. We've seen this in hydrolysis, aminolysis. So we've seen this before, right? The only thing that changes, so for the Claisen condensation, the nucleophile is going to be an ester-derived enolate. That's the only thing that changes. So suppose you start with a generic ester and you treat it with strong base. In this case, we use ethoxide. Ethoxide's not the strongest base imaginable, but it's chosen to avoid transesterification. You could also use a non-nucleophilic base like sodium hydride. The reason why we use ethoxide, just for everyone's reference, is that we're going to make a little bit of ethoxide anyway, so we might as well try to match bases and not have multiple different basic species floating around in solution. Anyway, so we make our enolate. We've seen these kinds of deprotonation reactions before. So now if we have another equivalent of ester, our nucleophile, this time our enolate, will attack the electrophilic carbonyl carbon, and lo and behold, we are going to make a tetrahedral intermediate. Now, you can really easily kick out your enolate. Sure, the Claisen reaction is reversible. This entire process is an equilibrium process. However, the productive pathway involves kicking out our leaving group ethoxide, and that in turn gives us our desired beta ketoester. Now, when we kick out ethoxide, we're now going to get to the very important key step of the Claisen condensation. Every step up to this point is reversible, but this next step prevents this reaction from undergoing retroclaisen processes. This next step drives the equilibrium towards the product and is non-reversible. In this key step, our ethoxide deprotonates our alpha position and we generate an enolate. This enolate is not electrophilic. Finally, if we treat with H3O+ during the quench, we can just protonate our alpha position, and that gives us our neutral isolable product. So, does everyone see how the Claisen reaction and the Claisen condensation mirrors a carbonyl substitution reaction? Does everyone see how the mechanism for the Claisen condensation is very close to a typical carbonyl substitution? The only catch is, just like the Aldol reaction, there needs to be a key step which drives the equilibrium towards the product. And that key step is the deprotonation of our beta ketoester to give a non-reactive, non-electrophilic enolate. Does this mechanism make sense to everyone? Okay, so just to talk about the step-by-step mechanism for the Claisen condensation. First, we form our enolate via deprotonation of our alpha position. Note the alkoxide base is chosen to match the ester alcohol to prevent mixed transesterification products from forming. If you use a different alkoxide equivalent, you're going to take the NMR, you're going to see 5 different peaks for 5 different compounds from all the transesterification products, and it creates unnecessary headaches. So you're better off using the same alkoxide as your ester alcohol to minimize undesired transesterification products. So once we have our enolate can react with electrophiles, in this case, another equivalent of our ester, and we form a tetrahedral intermediate. From here, this tetrahedral intermediate can collapse and we lose ethoxide. This beta ketoester is way more acidic than any other species that we have in solution. So it can be readily and irreversibly deprotonated with our alkoxide base to generate a beta ketoester enolate. Unlike the Aldol reaction, which is catalytic in base, the Claisen condensation is stoichiometric in base because the final deprotonation step makes a beta ketoester enolate, and this beta ketoester enolate is not basic enough to deprotonate our starting material, nor is it basic enough to deprotonate our alkoxide equivalent. So this drives the equilibrium towards the products because you can no longer generate an appreciable amount of alkoxide, and you can no longer engage this beta ketoester in a retroclaisen or another carbonyl substitution reaction. Does everyone see the importance of this last step? This is why pKa values are so important. Okay. So once you have this beta ketoester enolate, you typically quench it with an aqueous acidic workup. I would like you to note that if you want to try to trap this with an electrophile, due to the nature of the Claisen reaction, because you have ester enolates floating around in solution, generally we don't quench the enolate formed from a Claisen condensation with electrophiles. We usually do a separate reaction. Okay, so let's show the complete Claisen mechanism for the following substrate, just for our reference. So from start to finish, if we start with the following ester, just as a review, our first step is we're going to deprotonate our alpha position and make our enolate. You can also generate your enolate quantitatively if you're trying to do a cross-Claisen reaction. From here, our enolate will attack a second equivalent of our ester at the electrophilic carbonyl carbon, and we are going to form a tetrahedral intermediate. So far, this looks like what we've seen time and time again From here, this tetrahedral intermediate can collapse and kick out an equivalent of ethoxide. This gives us our beta ketoester. Are we done? Is this the full, complete Claisen mechanism? Have we explained why we get this desired product? Are we missing a step in this mechanism? Have we explained why we get this product in large amounts? We're not done yet. Would anyone like to provide and explain the last step? What's our last key driving step? What step drives this reaction towards the product? H plus quench is not quite yet. The key step for the Claisen reaction that drives this equilibrium towards the product is a deprotonation step. This in turn quenches out our formed equivalent of alkoxide, and it makes a relatively non-reactive enolate. This enolate cannot be attacked with nucleophile. And then when we quench, we can isolate our desired beta ketoester. So this proton transfer step is key to removing the equivalent of nucleophilic alkoxide floating around in solution. Otherwise, what we can see are what are known as retroclaisen reactions. So let's show what happens. Let's show what happens under a retroclaisen process. So suppose that you are not able to perform this deprotonation step. Suppose rather than a proton, we have an R group present. Well, if we think about this carbonyl, for a moment, this carbonyl is relatively electrophilic, right? So then if we have ethoxide floating around, then ethoxide, being a nucleophile, can easily attack the carbonyl carbon, right? And this is where things get really troublesome. Because when we form this tetrahedral intermediate, right? This is an equilibrium process. And when we collapse this tetrahedral intermediate, sure, we can kick out an equivalent of alkoxide, but we can also kick out our enolate, right? The enolate is a perfectly viable leaving group. And as a result, this reverts our Claisen product back to our ester starting materials. So if we don't have this alpha proton, if we don't have this key alpha proton that we can deprotonate to form this functionally non-electrophilic enolate, then our nucleophilic alkoxide can go in, attack our ketone carbonyl, and we can collapse and break our carbon-carbon bond to reform our starting materials. This is known as a retroclaisen reaction. Does this discussion make sense to everyone? Okay, so let's try to apply what we've learned for the Claisen reaction and the mechanism of the Claisen reaction to the following problem. So given the following starting materials, we're asked to predict the products from the following reaction. and draw a mechanism for the following reaction. And I know you just saw the mechanism for the Claisen condensation, but I find the best way to integrate a mechanism is to practice drawing out each step of the mechanism and noting the key features of each step. So let's take about 4 to 5 minutes to work through this example. And then I'd like students to share their proposed responses as a photo of their work in the chat, verbally, or annotated on the class whiteboard. So would anyone like to start us off here? You don't have to come up with the full mechanism at once. Just start from the basic steps. So we have multiple students noting we have these acidic alpha protons, and 2 students are drawing. Methoxide is going to immediately try to pull off this acidic alpha proton. Perfect. And now there's plenty of space on 2 sides of the whiteboard. So if you'd like, both of these students can continue their mechanisms on the left and right-hand side of the whiteboard, since it's great to see multiple students sharing their responses. So we deprotonate our alpha position and we make an enolate. So once we have our enolate, what will happen next? So once we have our enolate, it can attack a second equivalent of our ester, and that gives us a tetrahedral intermediate. From here, the tetrahedral intermediate will collapse and kick out ethoxide. From here, that generates our product, beta ketoester. However, we still have one more key step. So what drives this equilibrium to completion? Deprotonation of our alpha position. Exactly right. So we get our desired beta ketoester enolate, and then from there, we can quench it out with acid whenever we want. So from here, we can quench out our enolate with acid to give our desired beta ketoester. Though just make sure you don't heat it with strong acid or you're going to decarboxylate and then waste a lot of your time. It's not useless per se. You'd still form a carbon-carbon bond, but it's important to note that when you do the quench, mildly acidic conditions. So these proposed mechanisms look great. So let me just re-annotate them for our reference. So the way that I like to approach these mechanisms is just step by step. So we have an acidic alpha proton, we have a basic species, methoxide can pull off our alpha proton, and we can get our enolate. From here, this enolate can react with another equivalent of starting material. The ester carbonyl carbon is electrophilic, so we can attack our ester carbonyl carbon and form a carbon-carbon bond. From here, this tetrahedral intermediate can collapse, and the productive pathway involves kicking out ethoxide. That in turn gives us a beta ketoester. And then from here, as our key final step, we are going to deprotonate our alpha position to form our enolate. From here, during the quench step, we can treat with H3O plus to quench out our enolate and generate a neutral isolable beta ketoester. Does this mechanism look reasonable to everyone? Any questions on this mechanism before we move on? If we don't have any other questions, let's move on. So let's talk about a major substrate limitation. The deprotonation step with a formed beta ketoester is key to drive the Claisen reaction equilibrium towards the products. So if the formed beta ketoester lacks an available alpha hydrogen, the deprotonation step cannot occur and the equilibrium favors the reactant ester. So thus, it's very difficult to prepare these fully substituted beta ketoesters directly from the Claisen reaction. You're better off doing a Claisen followed by alkylation. Just to show the Retroclaisen reaction one more time, let's take a look at what happens with this substrate. So we have no available alpha proton. So if we treat this compound with any reasonably nucleophilic basic solvent, such as ethoxide, we're going to attack the carbonyl carbon. Why do we attack the carbonyl carbon of the ketone rather than the ester? What is more reactive in general, a ketone or an ester? The ketone, exactly right. So ethoxide will attack our ketone carbonyl carbon, and we're going to make a tetrahedral intermediate. Now, we can, in many cases, just kick out ethoxide for sure. This set of carbon-carbon bonds is relatively strained. We have a lot of steric congestion. So to relieve that steric congestion, or just as part of the collapse of this tetrahedral intermediate, we can break our congested carbon-carbon bond and generate an ester-derived enolate and another equivalent of our starting material. Does this mechanism for the Retroclaisen reaction make sense to everyone? Okay, so let's keep going now. And one application of this Retroclaisen reaction is that if you have a fully substituted beta ketoester, treatment of fully substituted beta ketoesters with nucleophilic alkoxide bases results in Retroclaisen products. So the Retroclaisen reaction, although often undesired, has synthetic utility. It's a method for decomposing carbon-carbon bonds and decomposing structures into simpler products. Though in most cases, the Retroclaisen reaction is not desired. It's often an undesired side reaction or an undesired outcome, because generally we prefer to form carbon-carbon bonds rather than decompose high-value carbon-carbon bonds. Nonetheless, it's important to note that the Retroclaisen reaction does have its synthetic uses. Does this make sense to everyone so far? Okay, so let's try to apply what we've learned, and let's try to predict the products of the following reaction and draw a mechanism for the following reaction. So this is an example of a Retroclaisen reaction. And what's pretty funny about this substrate is that the Retroclaisen can be followed with a productive set of Claisen reactions. So let's work through this example for about 4 to 5 minutes. And then I'd like students to share their proposed mechanisms and thoughts in the chat, verbally or annotated directly onto the class whiteboard. So what do we think? We have this beta ketoester. It's fully substituted at the alpha position, so we can't deprotonate. So what's going to happen if we have a nucleophilic reagent such as sodium methoxide floating around? So we have one student commenting that methoxide will attack our electrophilic ketone carbonyl. Yep, that's exactly right. from here, what will happen next? We have this tetrahedral intermediate. What are we going to kick out? So we're going to kick out our ester enolate. That's exactly right. And that in turn generates an ester product along with this congested ester enolate. Yeah, exactly right. Now, usually these kinds of intermolecular retroclaisen reactions are not very useful because once you make these retroclaisen products, you can have proton transfers and you just see a range of mixed Claisen products. So this is not very useful synthetically. The main showcase, the main point where the retroclaisen reaction is actually useful is when you have intramolecular reactions. So for example, you can use it to decompose ring systems. So for example, you can take like a 1,3-diketone and you can decompose it via a retroclaisen-like process. And that's actually pretty useful. So the retroclaisen reaction is often undesired. And that's why when you're planning your synthesis, you have to make sure to keep the characteristics and constraints of the Claisen reaction in mind. Sure. There we go. Any other questions on this mechanism? The student responses were great for this mechanism. Perfect. Let's keep going then. And let's talk about mixed Claisen condensations. Just like mixed Aldol condensations, we usually have to stack the deck in our favor. So mixed Claisen condensations are successful when one of the two esters acts as the electrophilic acceptor. And this generally works if one of the two esters has no alpha hydrogens and can't form an enolate. So for example, ethyl benzoate and ethyl acetate, ethyl benzoate has no alpha protons. And as such, it reacts cleanly to give a single Claisen condensation product. You can also apply the Claisen condensation to reactions between ketones and esters, right? Really, the Claisen condensation can be thought of as the reaction between an enolate and an electrophilic ester. So if the ester component has no alpha hydrogens, then we get a single mixed Claisen product. So we deprotonate our alpha position. And let's talk about this example for a moment. So we deprotonate the alpha position to the ketone. From here now, we have a pretty nucleophilic ketone-derived enolate. It can attack our electrophile, which in this case is ethyl formate. And that in turn gives us a tetrahedral intermediate. From here, this tetrahedral intermediate will collapse and kick out a ethoxide. And that in turn gives us our beta ketoester, which of course can be deprotonated. Now, one thing to note for the Claisen condensation is that we can get regioselectivity. So for example, if we have a substrate that looks like this, where we just have a methyl group on one side, and we treat it with sodium methoxide and ethyl formate, only one of these positions, alpha 1 and alpha 2, only one of these positions can productively react. Let's think about this example for a moment, and I'd like us to propose in the chat which of these two alpha positions is more reactive. Which of these two alpha positions can productively react in a Claisen condensation? And as a hint, I'd like you to remember our rule about when is a Claisen condensation product favored. And remember, we need to have an alpha proton after condensation in order to deprotonate, to drive the equilibrium towards the product. We have a lot of students typing alpha 2. To explain why, let's look at what happens for alpha 1 and alpha 2. So at alpha 1, we notice that we don't have a hydrogen. There's no hydrogen available. So we would see retroclaisen. Well, if we look at alpha 2, we have an available alpha hydrogen to deprotonate. So alpha 2 is favored. So this gives us a way to control the regioselectivity of the Claisen reaction via the fact the Claisen reaction is only favored if you have the driving deprotonation step. Does this make sense? Perfect. Okay, so just like we covered intramolecular Aldol reactions, there are intramolecular Claisen condensations. So intramolecular Claisen condensations work best with 1,6 and 1,7 diesters because we make 5 and 6 membered rings. As a general rule, 5 membered rings are great. 5 membered rings are a little bit better than 6, and everything else is pretty hard to make. 3 and 4 membered rings are not favored under equilibrating conditions in most cases. So the intramolecular Claisen reaction follows the same general Claisen mechanism. We deprotonate our alpha position. We usually do this on symmetrical substrates because if they're asymmetrical, you'll get a mixture of products, and that's not very fun. We make our enolate, and then our enolate attacks the electrophilic carbonyl carbon. Again, you may want to number your carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We get a 6-membered ring with a bond between 2 and 6. Our tetrahedral intermediate then collapses. We get our beta ketoester, and then we deprotonate the alpha position. And that gives us our desired beta ketoester enolate, which can be quenched to give us our neutral isolable product. Again, we can get regio control because the Claisen condensation is only favorable if you can get that deprotonation step to occur. Does this mechanism make sense to everyone? It's the same Claisen mechanism. It's just intramolecular. The only thing that students have trouble with for intramolecular reactions is that you need to make sure you're numbering your carbons. I commonly see students misnumber their carbons and end up with the wrong ring size. So always just make sure you're numbering your carbons and then filling in your structure from there. And I know what you're thinking. We're just forming a single carbon-carbon bond. That should be pretty straightforward. Let's try to practice what we've learned, and let's try to predict the product of the following reaction. And let's really practice numbering our carbons so we can properly draw the intramolecular Claisen product. So let's work through this example over the next 4 to 5 minutes. And of course, I'd like students to share their proposed responses in the chat, verbally, or annotated on the class whiteboard. So, would anyone like to share just their initial thoughts? This is a symmetrical substrate. Would anyone like to share their initial thoughts on what's going to happen in this reaction first? We have this diester. It's a 1,6 diester. We're treating it with sodium methoxide. What's the first thing that's going to happen if you treat an ester with a strong base? We're going to deprotonate at the alpha positions. Let's say alpha 1 and alpha 2. Does it matter what position we deprotonate at? Does it matter at all what position we deprotonate at? Nope, it's symmetrical. Exactly right. So we have our desired diester. Okay, so the students are telling me to deprotonate. Okay, so from here, what happens next? Would anyone like to try to continue on this mechanism from where we left off by annotating onto the class whiteboard? Or would anyone like to try and share their thoughts in the chat? What's going to happen next? So we have our nucleophilic enolate. Are there any electrophilic carbons floating around? Are there any electrophilic carbons in this molecule? The other ester, right? So we can attack our other ester. And I'd like a few students to try to draw the product, because the entire gimmick behind these intramolecular reactions is just making sure you're predicting and drawing the correct ring size. So would anyone like to try to draw out, or at least number the carbons before drawing out the ring system? Don't be shy to annotate on your carbon numbers or carbon labels on the class whiteboard before you draw your final ring product. Okay, so how many carbons are in our ring? What ring system are we making? So just counting our carbons in the ring, we're making a cyclopentane ring.
Okay, because there's 6, but one of them is exocyclic. Is that the right term?
Yeah,
okay.
That's why I generally start my carbon numbers from the enolate carbon to the carbonyl carbon, as it makes it easier for me to see what kind of ring size I'm making. And the beauty of this method is that you're able to draw your substituents out. So if you number this ring 1, 2, 3, 4, 5, you can put your substituents at the indicated carbon label. And that prevents you from mixing up the position of your ring substituents. So we have our 5-membered ring. We still have a tetrahedral intermediate. So what's the next step in this reaction? So we have this tetrahedral intermediate, and this tetrahedral intermediate will collapse and kick out our leaving group. Generally, intramolecular Claisens are more product favored than intermolecular Claisens. So would we be able to draw the next step where we kick out our leaving group? Yep, so we kick out our leaving group. We make our beta ketoester. And are we done? Have we finished this mechanism? Not quite. We have to deprotonate our alpha position. Just as a side note, this deprotonation step is even easier than the acyclic systems because as a general rule, the cyclic carbon-hydrogen bonds are more acidic. Perfect. So we have our beta ketoester enolate. And then we can protonate the enolate during the quench step. Perfect. So the student proposed mechanism looks great. So let's clear the annotations and let's finish drawing out this mechanism. So we form our desired carbon-carbon bond. So we have this tetrahedral intermediate. This tetrahedral intermediate will collapse. And that in turn gives us our desired beta ketoester. From here, we'll deprotonate our alpha position to drive this equilibrium. Well, there's a reason for that, because if you don't deprotonate, this ketone is electrophilic and it'll just immediately undergo retroclaisen reactions. It's important to acknowledge what the major species is in solution, because otherwise you won't be able to leverage that reactivity to get the desired product. So yes, it does seem weird that we protonate and then we deprotonate and then protonate, but it's important to note the deprotonation step occurs in the same reaction vessel, and it's why we don't see retroclaisen. It also explains why you need an entire equivalent of base. If you ever try to run a Claisen with substoichiometric base, you'll find the conversion stops. Like so? Did that answer your question? Perfect. Any other questions on the mechanism? Yes, the beta ketoester is much more acidic than the reactants. So the beta ketoester enolate serves as a sink. The beta ketoester enolate will never deprotonate your starting materials in an appreciable amount. Does that make sense? That student comment was quite observant. Okay, let's keep going then. And let's talk about what we can do with these beta ketoester products. Just like any other beta ketoester, we can now link the Claisen condensation to the alkylation and decarboxylation reactions we learned last chapter. This cyclic beta ketoester can be further alkylated and decarboxylated to yield highly substituted products. So this really shows how we can string reactions together to make very complex products. Does this idea make sense to everyone? Once we have this beta ketoester, we can take the beta ketoester, alkylate it and decarboxylate it and give substituted ketones. Any questions on this example? Okay. Let's talk about another reaction, which is a relative of the conjugate addition reactions that we've seen previously. This is known as the Michael reaction, and it describes the reaction of enolates with alpha beta unsaturated aldehydes and ketones to yield the conjugate addition product. So we've seen conjugate addition before. Our nucleophile attacks the electrophilic beta position. We form a bond and we generate an enolate. After a proton transfer, we are able to isolate our neutral conjugate addition product. We've seen this when our nucleophile is an amine. We've seen this when our nucleophile is a thiol, even an alcohol, right? We've seen this general conjugate addition mechanism previously, right? Does this look familiar to everyone? Does this look reminiscent of what we discussed in chapter 19 and 20? Now, by the same token, let's look at what happens in the Michael reaction where our nucleophile is an enolate. And more specifically, it's a stabilized enolate. So for example, a beta ketoester is a great nucleophilic enolate for Michael addition reactions. Okay, so let's show the mechanism for that. So suppose we have our beta ketoester derived enolate, and we react it with an electrophile such as methyl vinyl ketone. Not very fun to work with. These are lacrimators, so you have to be careful with the vapors. So our enolate, being a soft nucleophile, prefers to add 1,4. 1,2 addition is reversible in most cases. That in turn generates a conjugate addition product, and we generate the enolate derivative of our enone. So just to label our carbons here, I'm going to put a star next to the alpha position. Does everyone see the carbon-carbon bond that we formed when our enolate attacks and adds 1,4 into our beta ketoester? And from here, we can quench our enolate. But the reason why stabilized enolates are so wonderful for this reaction is, although this initial conjugate addition is reversible, when you have a stabilized enolate, or when you have a beta ketoester that has an available alpha proton after addition, is there something that we can do here? So we have this basic enolate, we have this acidic proton. So what will happen if we have a basic enolate near an acidic proton? And I'd like you to think what happened in the Claisen condensation. At the end of the Claisen condensation, there was a key driving step. What is that key driving step? So we have this basic enolate that we made after conjugate addition, right? That enolate's just sitting around. Yeah, because we have this acidic alpha proton, we're going to see a proton transfer. So we'll protonate our enolate and then deprotonate our alpha position. And this is why beta ketoesters are so great for Michael additions, because you in effect prevent the retro-Michael reaction or 1,4 elimination reaction from occurring. And then whenever we want, we can quench this reaction mixture with H3O plus and give our product. Does this mechanism for the Michael addition reaction make sense to everyone so far? Does this general mechanism make sense to everyone? Let's cover briefly the retro-Michael reaction or 1,4 elimination. So suppose we have a conjugate addition product. And we have our enolate. So in a retro-Michael reaction, we kick down and reform our enone double bond, and we regenerate our enolate. Does this mechanism for the Retroclaisen reaction, also known as 1,4 elimination, make sense? Perfect. Okay, so as we discussed, some of the best conditions for the Michael reaction involve using a beta ketoester or other stabilized enolate, reacting with an unhindered alpha beta unsaturated ketone. So just as a review for this mechanism, if we have, for example, ethyl acetoacetate and we treat it with sodium ethoxide, we can deprotonate our alpha position to make our enolate. For those wondering, why doesn't ethoxide engage in conjugate addition? It does, it's just reversible. So now that we have our nucleophilic enolate, enolates are soft nucleophiles. We have a stabilized source of electron density in our nucleophile. It's not like a organometallic reagent or a localized carbon-centered nucleophile. So this soft nucleophile will add 1,4 and we generate our enolate. And from these simple reactions, such as the Michael reaction, the Aldol reaction, and the Claisen reaction, you can actually string these reactions together to make really complicated products. So these are really the components for cascade reactions. Okay, so we generate our conjugate addition product, and then our conjugate addition product can be quenched with acid. Does this mechanism make sense to everyone? Perfect. So let's try to apply what we've learned now and make sure we're comfortable with the mechanism for conjugate addition of enolates. And let's try to predict the product from the following reaction and then draw a mechanism for this reaction. So in this case, we have a malonic ester and we're treating it with sodium methoxide followed by cyclopentanone. So as we work through this example over the next 4 to 5 minutes, don't be shy to share your thoughts in the chat, verbally, or annotated directly on the class whiteboard. Does anyone have an initial first step that they'd like to propose for this mechanism? We have this acidic malonic ester. We have sodium methoxide. So we are going to, it looks like the student's drawing that we're going to deprotonate our alpha position to make our enolate. Okay. Now that we have our nucleophilic enolate, it can react with electrophiles such as enones to generate conjugate addition products. Please draw the enolate double bond. So from here, our enolate can attack electrophiles such as our enone beta carbon. So would anyone like to continue on with this mechanism, or would someone in the class like to provide some assistance to the student drawing this out? So they form the enolate, and yes, perfect. So our enolate can attack electrophiles, such as the electrophilic beta carbon of our enone, and that can give our conjugate addition product. Perfect. So it's great to see students working together and stringing together the steps of this mechanism. So from here, we now have our conjugate addition product, and we have this enolate, and we can isolate our neutral conjugate addition product after an acidic quench of our enolate. So from here, we'll isolate our neutral conjugate addition product via protonation of our enolate. Yep. So the student proposed mechanism looks great. So let me just re-annotate. The beta carbon is more electrophilic in this context. And the reason for that is that when you have soft nucleophiles, there's a strong preference for soft nucleophiles to prefer to react at the beta position. Further, if we see addition at this carbon, that addition is typically going to be reversible. So even any 1,2 addition that we do observe, it's not as productive as 1,4 addition. The only main case where you see favorable 1,2 addition is when you have hard carbon-centered nucleophiles that can't be kicked out as a leaving group. Okay, so we have our malonic ester. We treat with methoxide, that in turn gives us our enolate. From here, our enolate can react with electrophiles, such as our electrophilic beta position of our enone, to generate our conjugate addition product. Now, if we really wanted to be clever, then we could string this reaction together and use this enolate for future reactions. So we can, for example, take this enolate and trap it with an electrophile. We can use this enolate for an aldol reaction. Really, the sky is the limit in that respect. But for now, we're just gonna quench our enolate with acid. So that in turn gives us our neutral isolable conjugate addition product. Does this make sense to everyone? Enolate chemistry is probably one of the most useful carbon-carbon bond forming transforms that we've learned in this course. Any questions on this mechanism? The student responses were great. Okay. So this is a good stopping point. So what we'll do is we'll take a quick 10-minute break. So let's archive this recording.